I'm going to show you a bug that has taken down real payment systems, corrupted real inventory counts, and sent real customers confirmation emails for orders that never existed. It hides in the most innocent-looking 2 lines of code you'll ever write. It's called the dual write problem. And by the end of this episode, you'll know exactly how to defeat it, with a pattern every serious event-driven system uses. Let's go! Here's the setup. Your service needs to do 2 things when something happens: update its database and publish an event to the broker so other services find out. Seems trivial, right? Save the order to the database, then publish order confirmed to the broker. 2 lines. But those are 2 separate systems, and you cannot make them atomic. Watch what happens when it breaks. You save the order to the database, success. Then you go to publish the event, and the process crashes. Now your database says the order is confirmed, but the event was never sent. Downstream, nobody knows. Inventory never decrements, the warehouse never ships, the customer is charged and gets nothing. Silent, permanent inconsistency. And flipping the order doesn't save you. Publish first, then write to the database. Now, if the database write fails, you've announced an order that doesn't exist, a phantom event. Downstream reacts to something that never really happened. Either way, you're broken. You need a real pattern. The pattern is the Outbox, and it's beautifully simple. The trick? Instead of writing to the database and the broker separately, you write the event into a special table called the Outbox in the very same database transaction as your business change. So it looks like this. Begin a transaction, update the order status to confirmed, and, in the same transaction, insert a row into the Outbox table describing the order confirmed event. Commit. Now, and this is the whole point, either both of those succeed together or both roll back together. There's no in between. Your database and your intent to publish are now perfectly consistent because they're the same atomic write. But wait, the event is sitting in a database table, not in the broker yet. So a separate process called a relay reads the unpublished rows from the Outbox and publishes them to the broker, marking each one as published as it goes. There are 2 ways to build that relay. The simple way is polling. A job periodically queries the Outbox for unpublished rows, publishes them, and marks them done. Easy to build, slightly higher latency. The better way is change data capture, and that's the second star of this episode. Change data capture, or CDC, means capturing every row-level change in a database as an event by reading the database's own transaction log, its write-ahead log, instead of polling. The most famous tool for this is Debezium. It tails the database log and streams every insert, update, and delete as an event. No polling, low latency, and 0 application code. So for the Outbox, Debezium watches the Outbox table and instantly streams new rows to the broker the moment they're committed. Here's the key mental model to state in an interview. The database is the source of truth, and the event gets published if and only if the transaction committed. No lost events, no phantom events. And because the relay is at least once, your consumers still need to be idempotent. The 2 patterns work together. Now, change data capture is bigger than just the Outbox. It has several killer uses. Beyond relaying the Outbox, you can use it to build read models or search indexes from an existing database with 0 application changes. You can use it to sync data across services or into a data warehouse or lake. And it's how you retrofit an event stream onto a legacy system that only knows how to write to a database. The monolith keeps doing its thing, and Debezium quietly turns its database changes into a stream that new services can consume. There's a mirror image pattern on the receiving end worth a quick mention. The inbox pattern. Just like the Outbox protects the sender, the inbox protects the receiver. The consumer records the processed message's ID in an inbox table in the same transaction as the effect. If a duplicate arrives, the unique constraint trips and the whole transaction safely aborts. That makes your idempotent consumer atomic even when the effect is a local database write. One last framing that scores points. Some brokers, like Kafka, offer transactions, but those give you consistency within the broker, topic to topic. The Outbox pattern gives you consistency between the broker and your database. Different tools for different boundaries. Say that, and you've shown you understand exactly where each one applies. So, dual write is the trap, the Outbox is the fix, change data capture is the engine that powers it, and the inbox guards the other side. Next episode, we go up a level, from consistency between two systems to coordinating a whole business workflow across many services, with sagas, event sourcing, and CQRS. See you there!